Okay, in this problem, I might have stated the tableau somewhat incorrectly. The way you're supposed to read the tableau is as follows. Each ton of input X yields 1/4 ton of A, 1/4 ton of B, 1/12 ton of C. That's the correct interpretation. And with that, of course, the formulation is meaningful. Okay? Some of you asked me that question during the break, so this is the answer to that. Okay, so let's go with more general formulations now. Typical application of linear programming problems arise in production planning when you've got limited resources and you want to produce different products while not exceeding the availability of those resources. So let's assume we've got M resources on hand and N activities or products. Each activity or each product consumes a certain amount of the resource, and let's take Cj to be the profit level for product J. Of course, these Cj's are given numbers, and then let's take Bi to be the available amount of resource I. And Aij is the units of resource I consumed by 1 unit of product J. When we say resources, of course, we mean things such as materials, money, budget restriction, or time restriction, or sometimes energy, labor, manpower, okay? And of course, when we say material restrictions, we may have different kinds of materials, and each different kind or each type of material could be a different resource, okay? So anyway, this set of M resources could be composed of any different combinations of various types of resources. And the basic problem here can be expressed as a maximization of the profit if you define Xj to be the number of units of product J to produce. Per planning period, where your planning period could be 1 day, 1 week, or whatever it is. Okay? So we maximize the total profit, which is your C1x1 up to Cnxn. By the way, these CJs may not be that easy to come up with, but that's the real world difficulties that you may face. Nevertheless, we're not dealing with that in this course. Okay? So just be aware of that. Things are not as easy as they look. Just obtaining the correct parameter values may be difficult in the real world. Now, the constraints will tell you that you're not supposed to exceed the available amount of resource I. So there's an upper bound here, and such a constraint will be written for each of the resources. On the left side, we have the total consumed amount of resource I. Now, resource I is consumed in AI1 units per unit of first product. So if you produce X1 units of the first product, that's your consumption of resource I due to production of product 1. Okay? The second product will consume AI2 per unit, but then you produce X2 units, so that's the total that comes from that portion, etc. So each one gives you that. Some of these AIJs could be 0, in which case, of course, nothing is consumed, but in that case, of course, such XJs will not contribute towards the left side. Then finally, we've got the non-negativity. That's a typical production planning problem in its simple core structure. Of course, when you do such production plans, there may be many other factors that you may have to consider, but we're not doing that here. Okay? So don't think that problems come as easy as they look here. Another typical example of linear programming problems arise in transportation context, but this is a very well-structured context that I'm going to talk about here. I'm going to assume you have a single product single commodity. Now, when we talk about a commodity, we don't actually mean a physical single commodity. We may mean, for example, suppose you're a manufacturing firm, Arçelik, for example, and you're distributing your products, various types of products, on a weekly basis to various distributors, okay? And you ship these products in truckloads. So whatever goes into a truckload could be cases of refrigerators or ovens or whatever you've got. We don't really differentiate these different products. For us, a single commodity is one truckload. That's it. So please, don't misinterpret these things. A single item or single commodity could be an aggregation of many different commodities. Okay? We've got a bunch of sources, 1, 2, say up to m sources, which means that you have your commodity being made available in these sources. These could be production units in different localities, could be distribution centers. You've got stuff in your depot, you're going to send them out, so on and so forth. And I'm going to assume I have A1 units of available units of the commodity under consideration in the first one, A2 units in the second one, AM units in the last one. These AJs are given numbers, okay? Supplies. In terms of, say, truckloads again. And then we've got places where we want to ship these products to. These are sinks. And let's assume we've got, say, n sinks. Since the product under consideration, or truckloads, they are uniform. They are not distinguishable. They are just truckloads. But if you had different sized trucks, for example, things could be a little bit different. Okay? we assume we have a one-size truck here, and they all go full load, which is a bad assumption probably. Nevertheless, that's the assumption. All right, so in this case, you can ship from any source to any sink. And if you cannot ship from a given source to a particular sink for whatever reason, administrative, or they are too far apart or whatever, just assign a very large cost to that particular leg of shipment so that that particular shipment from a given source to a prohibited sink is not permitted in your output, in your solution. Okay? So these things could be handled by assigning large penalty costs and so forth. So the sinks demand certain units of these products on a, say, weekly basis, and they are BJs. So these are your demands. And then in the middle portion of this picture, we've got the unit transportation costs, CIJs. So AI is the available amount, available supply at source I. BJ is the demand per time at sink J. Of course, this is also per time. And CIJ is the unit cost of shipment from source I to sink J. Unit cost meaning the cost per truckload. Okay? Your truck costs you something depending on the distance between the two locations as well as maybe other factors. All right. So what is the decision problem? The decision problem is to determine the amounts to ship from each source to each sink per time to minimize the total cost of shipment. That's the problem. And it's easy to formulate this problem if you define a double subscripted variable, xij, which stands for the number of units or the number of truckloads shipped from source I to sink J. So the problem we have is to minimize the total cost, which is going to be Cij times Xij summed over I and j. Let's just make this a double summation. I going from 1 to m, j going from 1 to n. Cij is the cost per truckload going from I to j. So if you're sending Xij truckloads from I to j, of course that's the total cost contribution for that leg of shipment. Subject to what goes out of the first source or the ith source. Let's just write it for the ith source. If you look at the ith source, you send xi1 units to the first sink. And then you send xi2 units from the same source to the second sink, so on and so forth. Then you send xin units from source I to the nth sink. So this is the total coming out of source I, and that, of course, cannot exceed the available amount at the source, AI. And such a constraint is valid for each of the sources. Let's meet the demands exactly. For the jth demand, I need x1j units coming from the first source, x2j coming from the second source, so on and so forth, xmj coming from the nth source, and that's going to be equal to bj. Now finally, we've got xij's being non-negative for all I and j. I going from 1 to m, j going from 1 to n. Now when you write it this way, you don't really see the structure. It's always good practice to envision the general problem first and then write down a small example to get the problem structure, because this problem structure business is actually what really counts when you wanted to solve these problems efficiently, okay? By exploiting whatever structure could be available. So for this particular structure, let's just do an example here. Before I do the example, to be able to meet all these demands, what is the feasibility requirement? Whatever amounts you've got available at the sources, the total, should be at least as large as the total demand. Okay? Otherwise, of course, you won't be able to meet the demand, at least some of them. So under this condition, this produces a valid or feasible solution, and it will produce an optimal solution as well. Without that assumption, it won't work. Typically, these problems are formulated with the assumption of equality between the total supply and the total demand. That's called a balance problem, but that's a side issue right now. So under this assumption, things will be feasible. Okay? So here's an example. Suppose I've got 3 sources and 4 sinks, and you've got 80 units available here, 100 units here, and 50 here. You demand 40 here, 60 here, 20, and 30. Is this feasible? It is, I guess. Yeah. Let's also assume certain costs here. The cost is 5, 10, 13, 4, 2, 20, 6, 10, 15, 6, 11, 12. I don't know, I just made up those numbers. I hope they make sense to you. Okay. So in this problem, I'm going to minimize 5 times x11 plus 10 times x12, and I'm a little bit lazy now. This is the second lecture, so you can fill in the blanks. The last one will be 12 times x34. Okay, that's your objective function, the total cost. Subject to 3 supply constraints and 4 demand constraints. The first supply constraint will be x11 plus x12 plus x13 plus x14. That's the total coming out of source 1. That should be no more than what you've got available at that source. Second one, x21 plus x22 plus x23 plus x24 no more than 100, and x31, x32, x33, there's some no more than 50. These are your supply constraints. And then what goes into number 1 sink is x11 coming from the first source, x21 coming from the second source, and x31 coming from the third source. That should be equal to 40. Why am I writing these down in this structured fashion? Because each variable is associated with a column. You know, remember the first 2 lectures we talked about that, columns being associated with variables. Okay? So it's always good to keep that in mind. Columns and columns of the matrix on the left and variables, they are always hand in hand. The second column, x12 plus x22, the second sink, by the way, x22 plus x32 equals 60. The third sink, x13, x23, x33 equals 20, and x14, x24, x34 equals 30. And finally, your non-negativity constraints. Okay? All right, now you can see the structure. Ones, 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 and 1, 1, 1. You know, I'm talking about the coefficients here rather than the variables themselves. The coefficients are either 1 or 0. And in a given column, you see 1 here, 1 here. Elsewhere, you've got all your zeros. This is the typical situation with network flow type of problems, 1 and a -1. In this case, if you multiply the last 4 constraints by -1, both sides, you will have +1, -1. This is known to some of you, perhaps not known to some of you. Nevertheless, that's a situation where you can actually specialize your solution algorithm tailored to that particular structure to make it much faster. Okay? That's called a network flow type of structure. And transportation problems are a special type of network flow problems. Just keep that in mind also. Towards the end of the course, we will actually look at some minimum cost network flow problems, one of which is a special case, is a transportation problem. At that time, maybe you will remember that. Okay? Okay. In the first chapter of Bazara, Jarvis, and Sherali, there is an example problem on tanker scheduling, which I'm not going to cover in class. Nevertheless, it's a good example where things that may look quite complicated may actually be efficiently or innovatively formulated. And when they formulate this problem, Danzig is the one who formulated, as far as I remember, the father of linear programming. it turns out that because of the innovative formulation, it comes out as a transportation problem structure, even though at the beginning, you don't really envision it that way. So that really helps for solving the problem. So look through that carefully, and you never know. Maybe in the exam we may ask a question or something on that, and you would be familiar with that. Let me talk about a production control problem here. There's also a good study, a case study, a real-world problem in the first chapter of the second recommended book by Bertsimas and Chiklis. And in that problem, that's an actual problem that arose in 1988 in DEC, Digital, what was it? DEC, Digital Equipment Corporation, something like that. Okay, that's a numerical problem, but it involves many of the uncertainties of real-world problems. It's well illustrated. So get the book and read through that also. My course, this course, is not really focusing on formulations. So for that reason, I'm sort of just mentioning these things. You should do the groundwork on your own, okay? Because we're going to focus on the structure of linear programming, geometrical as well as algebraic, and that's what the primary material of the course will be on. This production control is also from Bazara, Jarvis, and Sherali. Again, it's for a single item, which may be an aggregation of many different items. Okay? For example, cases of beverages, where each case may actually, or cases may consist of Coke, beer, or whatever else you may think of, okay? Fanta, etc. Now, this is going to be on the record, so I'm not advertising anything, but these are some of the things you could think of. All right. Suppose we have a planning horizon of 0 to t. And let's take this in continuous time, okay? It's not in discrete time. You have a function g as a function of time, small t. This is the demand rate at time t for the product under consideration. Let's define x of t. This is known, either in functional form or in whatever form it comes, okay? X of t is a decision variable. It's the production rate at time t. This is your control variable. EEs are quite familiar with control problems, but IEs have no idea what control problems are. Anyway, this is a simple-minded example of that, okay? What's a control problem? Just in a few words, you've got some kind of a system. It undergoes certain states, and you don't want the state of the system to fluctuate too wildly. You want to keep it within certain limits. And to do that, you want to use a control variable, whatever is under your control. You want to play with that so that that control variable makes the system respond in a certain way. That response will be the dependent variable, so the response will be within the limits you are looking for, okay? So that's the type of control problem we're talking about. So this is an example. Y of t is again a decision, well, it's a dependent variable. This is the inventory level at time t for the product under consideration. So this is your control variable, this is your state variable. This is what you want to keep under control. In other words, not too much fluctuation, okay? Why? Because the stuff that you keep in inventory, you keep these things in a warehouse or in some warehouse space. So if things fluctuate too badly, you will run out of space. And also, you might want to keep a minimum inventory level to be able to respond to customer needs whenever there's such a need. So minimum inventory should also be a lower limit, typically. Okay? You don't want it to be 0. All right, y of t. I'm going to assume the initial inventory is given. This is the initial inventory. If you're doing this planning stuff from 0 to t, then from t to, say, 2t, etc., each time zeroing the time, the clock at the beginning of the period, whatever is left over at the end of this planning horizon will become the initial inventory for the next planning horizon. Okay? So just think of it that way. Yt is your final target inventory. If there's a target. If there's none, you may make it a variable. These are also known, or you specify it numerically. What else? Let's assume we have a simple-minded cost structure here. C1 is the holding cost per unit stored per unit time. In other words, when you keep stuff in your warehouse space, it occupies space, and so that space is no longer available for other products, which means it's costing you something, okay? And also, when you keep it in inventory, things may go may undergo spoilage, or maybe stolen, or something lost. These things always accrue certain costs. So C1 includes all of that. C2, production cost per time. Per unit time, okay? And B1 and B2, these are your control limits, upper bound on the production rate, and B2 is the upper bound on the inventory level. I don't have any lower bounds in this case. The lower bounds are natural lower bounds, which are 0. Okay? All right, so here's the problem. Well, before I state the problem, let me just draw a picture here. This is the time axis. Your production will be something along the time. Okay? This is your production, some kind of a function. We don't know what it is going to be. Nevertheless, this is what you would get. And when you want to minimize, the cost will consist of the holding cost plus the production cost. Now, the holding cost will be, what is the C1 times Y of T, the inventory level at time T, dt. And when you multiply that with C1, that's going to be the C1 times dt. dt is a little time increment. Okay? C1 times dt will be the holding cost per that length of time. And then when you multiply it with the inventory level, that's how much you actually accrue as cost. Of course, you integrate this from 0 to t. That's your total cost. I hope that makes sense to you. Okay? When industrial engineers see integrals, they sort of shy away from that. But we've got some double E's here. I guess they don't shy away. Anyway, you get familiar also. The management people, I don't know. Do you guys like integrals or not? Huh? Who are from management here? Huh? You're neutral? Okay. Okay. There's a second integral here. What's the second integral? For the production. C2 times x of t dt. Again, C2 times dt will be the cost of production for that length of time times, of course, what you produce, the amount you produce, going from 0 to t. This has nothing to do with linear programming yet. Okay? Subject to constraints. Now, what you have in inventory at time t is going to be a function of what you had at the very beginning, which is y0, plus what you produce up to that time point, x of t, about x of u, du. This is the total you produced up to that time point, minus what you consumed, or the demand amount up to that time point, which is g of u du. So that determines what y of t will be at that time point. Of course, such a constraint is written for each t in the planning horizon, which means an infinite family of constraints. Okay? It's easy to write it down, but when you work with digital equipment, computers, these things may become quite difficult. All right, what is the target inventory? That's the inventory at time t. We want that to be equal to the target inventory, whatever it is. That's a simple constraint. And then we want x of t to be greater or equals 0, but never exceeding b1. This is again for each time point. And then finally, we've got y of t bounded below by 0, bounded above by b2. Okay. Okay, just a minute. Yes, what is your question?
Shouldn't we say greater or equal to for the first question? Because if, for example, demand exceeds the first constraint.
This one, I see.
Because if the demand exceeds the items on hand, then we will have negative inventory.
This is a dependent variable. So the answer is no. This is a dependent variable which depends on two functions. The production function, so things will accumulate when you produce, plus of course what you had. And this is the consumption function. Things will be extracted or taken away from your possession. So it simply expresses what you would end up with when you have so much production and when so much consumption plus the initial inventory at up to time point t. So in that sense, we want to write an exact relationship rather than inequality. Okay? And of course, we're trying to keep the inventory between bounds. It's a control problem. We're not trying to meet certain demand. We're trying to keep things under control. And x of t, of course, should be also between certain bounds. Okay? All right. So how do we do this using linear programming? We do what many people do. We discretize the problem. Rather than using a continuous time version of the formulation, we discretize it. How do we do it? We take the time horizon and we divide it into, say, equal length slots or segments. They don't have to be equal length. Nevertheless, let's just do it equal. Each one has a length of delta. So the length of one particular period is delta. So let's assume we have period 1, period 2, 3, so on and so forth. Let's assume this is the nth period with n times delta being equal to t, capital T. Okay? And I'm going to assume that things are pretty much constant during each period, or within each period. So xj will be the production rate in period j. So we produce a constant amount during the jth period, whatever xj happens to be. Okay? Whereas in the continuous version, it could be changing within the period itself, or within that time segment. Now, Gj is your constant demand rate in period j. How would you compute that? And Yj is similar. Yj is your inventory at the end of this. This is the inventory at the end of period j. Just for the Gj, what's the average demand rate in period j? Actually, it may be varying during the period. So if you look at the jth period, you've got some kind of a demand function here. This is your G function. But then we want some kind of an average demand here. Okay? So you can compute the demand here. You can compute the demand here and take the average. That would be an approximation of what you want here. Or you can simply integrate your G of t in this segment. So if you integrate G of t in that segment, you would get the total demand here. And then you would divide it by the length of the period, which is your delta. Okay? Where do I integrate from? To where? This is period j. So I've got delta j here. That's the time point corresponding to the left part. And the time point corresponding to the right part is j plus 1 delta.
J minus 1?
Pardon? No, I think it's this way. See, for the second one, for example, it will be, oh, I see. Let me just check. I don't know. If j is 2, yes, I think you're right. Yeah. Anyway, you can figure that out. It's a minor point. But from the beginning to the end of that period, so be careful with what you're doing. Okay. So in that case, we want to minimize the total cost, which consists of two summations now. C1 delta times yj, that's the inventory cost. Of course, C1 times delta is your inventory cost for the length of period, okay, for that length, delta. Plus, and you can call that Cj if you wish, but you know, it's a priori computed using C1 and delta. And the second one will be C2 delta xj. Subject to what you have in, let's see, yj is the inventory at the end of period j. So at the end of period j, you have yj. That's going to be what you had at the beginning of that period, yj minus 1, plus what you produced, that's your xj, minus what you consumed, the average demand, of course, multiplied by delta. Okay? So this constraint tells you how to connect the jth inventory period, jth period inventory level to the previous inventory level, rather than connecting the initial inventory to the time point t. We made a switch of viewpoint here. All right, the next one is, the last one will be the target inventory, and xj's are bounded below and above by 0 and b1 respectively, and yj's are bounded below and above by 0 and b2 again respectively. That's a linear programming formulation of this problem. Of course, this is approximation. Because you're discretizing, things will be approximate. The smaller delta, the better your approximation is. But then the smaller delta, the more variables you have, the more periods you have. So you find the trade-off accordingly. Okay? All right, let's stop here. Next time on Wednesday, I'm going to start talking about the structure of linear programming in terms of geometry, and then we'll just carry on. Okay? See you.